And we discussed the fact that splay tree search is done using a find operation where you descend the tree. And then you splay the sought item to the root. And we spent a bunch of time doing analysis that showed that this was amortized O of log n to perform the search. And that is because it was amortized order log n to perform the splay, and the find, the descent, is cheaper than the splay itself. We also showed lots of other bounds simply by changing the potential function that we use, changing the W, the weights that we associated with the different nodes, right? So that's what we did last time. I should have checked. People hearing me okay? Yeah, okay. But we still also want to think about insert and delete, right? So how do we do those in a splay tree, and what is the resulting amortized time bound for doing these operations? So these are just binary search trees, right? And so we could just use standard insert and delete operations from a binary search tree. Would that be a good idea? Anybody there?
Well, wouldn't you want to just do this like insert and then splay, delete and splay?
Good. Okay, so splay should probably be involved. How come? What if we just did standard insert or standard delete?
Or for standard insert, at least you could just end up with a long chain, and then your inserts will take a long time.
Exactly, right? If we don't splay, we're going to be in trouble, right? So if we do a sequence, one of the bad cases in standard binary search trees is if you insert the items in order, then you end up with a linked list. And each insertion is going to be walking down that linked list, and so you end up spending n squared time just inserting n items. So we need to splay. And it does work to just combine insert and delete with splaying in the obvious way. So what you can do is insert, then splay, right? And that does have an amortized runtime of order log n. Now you have to be a little bit careful in thinking about how you prove that, right? So we prove that the amortized cost of the splay operation is order log n. But what do we have to be careful about if we want to argue that the cost of the insert is also order log n?
About the new potential that you have introduced?
Right. So, I mean, the insert operation itself, that walking down the tree, just like in find, that's paid for by the splay operation that we perform after the insert. However, because we've inserted a new item, that new item adds potential. To the tree, right? And it could conceivably add a lot of potential to the tree if it's at the bottom of a long path. So you have to be a little bit careful in your analysis. For delete, it's even worse because, I mean, if you're deleting an item, what should you splay in order to pay for that deletion? Maybe you splay a neighbor of the item you deleted or something like that. But it turns out that there's a much cleaner way to talk about updates to splay trees. using some alternative operations. Okay. One operation called split, where you take a tree and a node X, and it returns two trees. One of which consists of the items less than or equal to X, and the other consisting of the items greater than X. Okay. And so that's kind of like a deletion. There's a converse operation of join, where you take two trees such that all of the items in tree T are less than or equal to X, and all the items in tree S are greater than, our items in T are less than X, and items in S are greater than X, and it returns a tree which is the union of the items. Okay. And what I'm going to show you is that these two operations are very easy to analyze as splay tree operations, and also that you can very easily implement delete and insert and delete using them. Okay. So let's talk first about how you implement split. So I've got a tree. Let's assume X is in it, although you can use the successor of X if X is not itself present, or the predecessor of X. How can we split the tree into two trees with the smaller and larger keys?
We splay X first.
Exactly. So we splay X. So now we have a tree X with two subtrees A and B. And then the split is straightforward. We just pull off the right subtree, and we have completed the split. Right? So what can we say about the amortized time for this split operation?
It's just log n, right?
Yeah, right. This is order log n amortized to do the splay, right? And then notice that if we're splitting a tree, if we're taking a subtree off of another tree, the change in potential is negative, right? The potential in the two trees that we get is less than the potential of the tree that we started with, because the rank of the root decreases and nothing else changes, right? And I'm doing the obvious thing of taking the potential of a collection of trees to just be the sum of the potentials of the individual trees, okay? What about join? Well, join is even more obvious how you do it, right? You just make X the root of a new tree, right? And that doesn't even require a splay. You just put X there at the root, right? Sorry, let me just think for a sec. I may have confused you. Where'd my eraser go? Let me make a change to the join operation to not specify an X, but to just refer to two trees. that I want to join. So in this case, implementing join does require a splay. What we'll do is we will splay the minimum element of s to the root so that we have an s over here, and then we will just attach t to that s, right? So one splay again, display. And what can we say about the change in potential here?
It increases.
It certainly increases, which is bad for us, right? Because an increase in potential has to go into the amortized cost. But why isn't it too bad for us? So how does the potential change from our two trees to our combined tree?
Only the root increases in potential.
Exactly. Only the root changes in potential. If I'm looking at the potential after the splay, right? And at worst, the root now has n new children, and that means that its rank, which is its contribution to the potential, only changes by log n. Okay? So both the split and the join operations emerge completely naturally from splay trees, right? You just do a splay and then you attach it or cut the tree, and they both have order log n runtimes amortized. So now that we've got those two operations, how do we implement split and join, insert and delete?
We split at x first.
Yep. And that's giving us, say, an A and a B. We'll assume X is not already in A. Now what do we do?
Make X the new root.
Yeah, we can just put X as the root of A and B, but if I want to talk about it in terms of my other operations, I can join A to the result of joining X with B. Right? So one split and two joins. We've argued that split and join are both order log n, so we're done. What about delete X from T?
Would you just split X and T and then like join the remaining subtrees that are resulting?
Exactly. Split T at X. Again, it gives us A and B. Actually, the way we defined it, notice that X will be in A, right? Sorry, again, I sort of gave you two different I'm working with two different definitions of split and join at once, which is a bad idea. So here we're going to have A less than B, and X will be at the top of A because of the split that we just did, right? And so now, oh, sorry. No, this is right. But what we do over here is we split t and x at x, and this gives us a, but with x still on it, because that's the way the split is defined, right? And then also b, and then we just join a to b, right? So again, one split, one join, or you could think of it as two splits where we're splitting off x. And overall, these both take order log n time. So that's the end, right? I've now shown you how to do both of the operations we care about in order log n time. And along the way, I showed you how these two other interesting operations of splitting and joining splay trees, which actually turn out to be pretty useful in some cases, and also take order log n time, okay? So to wrap up with splay trees, a few implementation details. First of all, there's a nice little section of the paper that talks about top-down splaying, which just buys you performance in practice. It shows how if you're going to be splaying an item to the root after you find it, you can actually perform the rotations on your way down, so that when you finish and have found the item, you're also already done with the rotations and you don't have to walk back up performing those rotations. And that can improve your performance by a constant factor. Other things that you might want to consider doing in practice is to splay only if you have a long path. Okay, why might this be a good idea in practice? Well, let me first ask why this not be a bad idea. Why doesn't it hurt you to only splay when the path is long?
Because if it's not long, that kind of takes away the whole kind of purpose of splaying. Like the path is short.
Yeah, I mean, it not only takes away the purpose, but it takes away the need for it, right? If the path is short, then you can just count the real cost as the cost of that operation. You don't need to pay for it with anything. So as long as you only spend log n time on a search, you don't need potential for it. And so you don't need to draw potential out of your tree. So that's why it doesn't hurt. Why might be a good idea? And this starts to get at what is the one downside of splay trees compared to other tree data structures.
When you have a long path, it's more likely that it's unbalanced. But if it's a short path, like you might be like unbalancing it.
So yes, as you will see in your homework, right? Sometimes splay operations make a tree more unbalanced. And you could argue that splaying a short path is a bad idea because it's just going to unbalance the tree, right? But the potential function tells you that it's not too bad a thing to do to splay all the time. But why might splaying all the time be a bad idea in practice? So this has to do with the architecture of modern machines. So a downside of splay trees is that lookups cause writes. Right? When I look for something in the splay tree, it causes me to change pointers in the splay tree. And in modern machines, writes are much more expensive than reads. How come? Come on, this is MIT. You can't all be theoreticians.
I guess writing to memory is slower than just like reading something.
Yeah, so what's the difference? Well, the difference is, again, caches, right? Data gets cached, and if you have cached data, then it can be read quickly. But when you write data, then in order to obey this semantics, right? When you write data, it's supposed to get written, and that means you have to put it to memory, right? And so even if you have great caches, you're paying for a write to memory, and that's a big cost compared to reads. So you don't want to write too often, and splay trees are bad for that. They also are bad in terms of locality of reference because they keep moving things around, which makes it hard for the caches to do a good job. And so in addition to only splaying if you have a long path, another thing that you might do in practice is only splay for a little while. Okay, so you know, as you start up your computation, you use the splay tree at a splay tree, but at a certain point you just freeze it and keep using it in its existing structure. Why might that be a plausible heuristic?
Well, assuming that like after a while, like assuming that like the probability distribution of like what your queries are doesn't change, then like after a while, like your splay tree will already roughly follow that, like things that are more
Exactly.
commonly accessed will already be
Exactly, and that's actually the notion of probabilities definitely plays a role here. So if you imagine a computation which involves randomly accessing items with certain probabilities, you remember last time we showed that splay trees are optimal for this kind of search, for this kind of distribution where the access time for item X is minus px log px, which is optimal. And intuitively, the way it's doing this is by pulling the frequently accessed items to the top through splays and leaving the rarely accessed items at the bottom. So if the accesses are truly random, then you figure that after some splaying, the important stuff will be at the top and the unimportant stuff will be at the bottom. And so now you can just keep using that tree and you don't have to keep changing it around anymore. Of course, if your access pattern changes later, if there is not randomness, if there's a history dependence or just an evolution over time, then you might have ended up with a tree that was good for the beginning, but is very bad for the end. So this is a somewhat dangerous heuristic to use, right? Splaying only on a long path can never take you too far from a good outcome because you're never spending more time than you needed to. But this other one of stopping after a while, that can be dangerous. I wanted to mention one other thing that I forgot to mention last time, which is pretty interesting, and it bears on the question somebody asked about sort of entropy in data structures and using information, which is another surprising use for splay trees is as a compression algorithm. So what you do is, you store your items, you suppose that you want to compress a sequence of characters. What you do is you store them in a splay tree. But then instead of sending a character over your communication link, you send its path in the tree. So you take your tree and you search for that character in the tree, and this gives you a series of zeros and ones depending on when you go left and right. Okay. And then you splay the character to the root of the tree. Okay. So that means that the number of bits that you send is equal to the search time. Right? And we argued last time that in various ways that splay trees kind of optimize the search time, and so they will similarly be optimizing the number of bits that you send for each character. And so there's sort of an interesting trick for using a data structure to do an information theoretic thing, which is compression. So that's the end of splay trees. Are there any questions about them before we go on? All right, so the main topic for today is buckets or indirect addressing. So far, all of the data structures that we've looked at were pointer based, right? Our Fibonacci heaps, our persistent data structures, and our splay trees all fit into this pointer machine model where you have fixed size nodes in your structure and they point at other fixed size nodes. Today we're going to talk about how you can take advantage of arrays, right? And so, some basic arithmetic to decide where you want to look in your array. Now, we actually already took advantage of arrays because our implementation of persistent data structures used an array, even though our data structure, even though we were simulating a data structure that did not use arrays. But if you think about it, the way that we used that array, we could have used a binary search tree instead. So everything that we've done so far could be done with pointer-based data structures. But now I'm going to show you something that really relies on arrays. And we're going to go back to shortest paths. But I'm going to look at a special case. I'm going to assume that all of the edge weights are integers in the range from 1 to some large constant c. Okay. So this is a restriction. So I can use any of the existing shortest path algorithms to find shortest paths, even when the edge weights are small. But I'm going to show you that you can do better when the edge weights are small. Okay. So what can we observe about shortest paths when all of the edge weights are small? How might this be easier or more of a special case than general shortest paths?
If edge weights were just 1, it's just BFS.
What was that?
If edge weights are 1,
if
it's
the edge weights are all 1, that's a great way to start for intuition. So what do we do to find shortest paths when the edge weights are all 1?
It's BFS.
BFS, right? We no longer have to distinguish edges. We just need to know what's connected. So if C equals 1, then we can use BFS. And this is order m time, right? Remember that shortest paths in general is order m plus n log n if we use Fibonacci heaps, or order m log n if we use standard binary heaps, right? But if the edge weights are 1, all of a sudden it's order m, right? That log factor went away. Can we generalize that at all?
We can get O of m times c if we replace an edge with the weight n with like a bunch of small edges.
Great. So if we make an edge of weight w into a chain of w edges, right? Now we have an order m times c time bound, right? Which, again, it beats m log n if c is a small constant. It's going to be more problematic comparing it to order m plus to n log n, right? There's going to be some constant value of beyond which of c beyond which this loses to Fibonacci heaps, right? But it still is pretty appealing because of its simplicity. But of course, we don't actually want to replace edges with vertices. We just made our graph much bigger. We'll need more storage. But the thing to remember is they don't really have to, right? We can just remember sort of how far along the edge we are as we do the BFS. So that's not a big deal. But let's work on improving things still further, okay? Let's go back to our heap idea and ask, is this heap special? If we're running Dijkstra's algorithm, or sorry, not heap, but priority queue. If we're running Dijkstra's algorithm, and we're looking at the priority queue, what are we going to see? Well, the values in it are small integers, or are integers, not necessarily small, right? Now, another really important characteristic of this priority queue for Dijkstra's algorithm is that it is monotone. The min is non-decreasing. Right? Because the min is always the distance of the thing I haven't added yet, and it's farther away than all the things that I've added, or no closer. Okay. So I'm going to try and make a specialized priority queue for this case. Okay. How might I do that? Well, Dial came up with a method of just using an array for the priority queue. It's a pretty big array. And what you do is you make a collection of buckets. And you put in bucket D, you put all of the items of distance, or of current distance, right, or distance estimate. D. So if I start at 0, right, at the start of the algorithm, I'm just going to put S, the source of the shortest path tree, into the 0 bucket, and nothing else is going to be anywhere. So now what do I do for Dijkstra's algorithm? I take the source and I look at its neighbors. And now I am going to start inserting neighbors of S into places in the appropriate buckets, right? So I remove S and I insert my neighbors. Now, what do I need to do for the next step of Dijkstra's algorithm?
We find the minimum.
Yeah, I have to find the new min, right? So if my items are stored in buckets in an array, what's the obvious way to find the new min?
Keep moving. Yeah, keep moving forward until you hit something.
Yeah, by a forward scan. Right? All right. How long is that going to take to find that min?
Excuse me, can't we just save the minimum index of the
We just
array?
save what?
Can't we to make the runtime of forward searching shorter? Can't we just save the minimum index that is not empty in the array?
Save the minimum in what?
Save the minimum index of the array which has non-empty, which is non-empty.
Good. So initially that's 0, right? When we have the source here.
Right.
So now we remove the source, and now we're going to scan forward, and we're going to find this. We're going to find this next node, right? So what is that? What you mean by saving the index? Is just by knowing that we're here?
So actually, we have to put the the value of the neighbors of the source in the array, right?
That's
You have to
correct. Right, so after I remove the source, I'll insert these neighbors of the source, and now I need to find the next min, which means scanning forward from 0 to find the first element in the array. Now, it's true that as I'm inserting the neighbors of the source, I could just see which of them is minimal.
Right.
But what happens next time? So I get to this closest neighbor of the source, I add it to the shortest paths tree, and now I need to insert its neighbors.
Right.
Right? So, you know, they might go here, right? But now I need to find now I need to remove this element and find the next min. Now the next min might be one of my neighbors, but it might also be one of the source's neighbors, right?
Yeah, but I mean, we can keep track of the minimum when we are adding the neighbors of this node.
Yes, so maybe this is the smallest node of the neighbors that I've added, right? But how does that help me? Because you notice that there are smaller nodes that
No, I mean
were neighbors of the
compared to
source.
the. Oh, I see. Right.
Right, so remember in Dijkstra's algorithm, I have to keep taking out the minimum distance, and it might not be a neighbor of what I just looked at.
Right. No, I was gonna say like to keep track of all of them, but then we can't, like, because when we remove
Exactly, there's going to be lots and lots of these different weights in here, and I mean we need the data structure to help us keep track of all of them, and we can't have them all at our fingertips.
Right.
So after I have found the second one and deleted it, I need to scan to the next minimum, right? So how do I find that? Well, I could again start the scan at the beginning and move forward until I get to the first non-empty bucket. But here's where I can take advantage of the special property of shortest paths, right? So do I need to scan from 0 again to find the smallest element?
No, you can start at the one where you ended before.
Exactly, because the heap is monotone, I know that the next value is going to be to the right of whatever I deleted. So I just continue the scan from the previous deletion. So basically I repeatedly scan to the min, remove it, insert the neighbors into buckets, and then go back to the beginning. But what's crucial is that the next scan starts from where I just removed an element. Okay. So what's the time for this algorithm going to be?
Longest possible path times the number of edges.
Longest path times number of edges. So that
No,
is
just the longest path. Yes.
Well, plus the number of edges, right?
plus the number, right? There's two things going on, right? There's neighbor updates. Which cost me order M because each edge causes one update, right? Notice that an update might involve a node that's already in my priority queue. So when I look at an edge and update a distance, I might actually have to remove a node from its current bucket and put it into a closer bucket, right? But it's certainly linear and the constant is great. The other cost is the scans, right? And as we observed, right, scans only go forward. We never have to back up. And how far am I going to scan? Well, I'm only going to go up to the max distance, right? Because that's where I'll find the last element that I need to put into the shortest path tree. And so that bounds our overall runtime by M plus the maximum distance, which I'll denote by capital D. Okay. So our runtime is order M plus D. And on top of that, the simplest imaginable data structure, right? We don't have to implement any kind of priority queue data structure. We just scan an array. Can we bound D by some other parameters? Well, remember that I said that the largest edge cost is going to be C. So what does that tell me about the maximum distance?
It's ONC.
Exactly. It's at most NC because your longest path can only have N edges on it, and you can only have C weight per edge. So it's N plus NC. What about the space? Well, this is going to be order N plus D, or order NC, right? I'm assuming that I'm not counting the graph itself in the space. You can assume that you have read-only access to the edges, but we don't actually have to store any edges. We just have to store the N items with their distances. Plus, we need that array. But can I do a little better here? Do I need an array that's this big?
No, you can have it somehow be like only from the smallest entry to the biggest entry.
Yeah, so what is the range of values in the array at any given time? At any time, the non-empty buckets range from some current value D. How far can they get? How big can you get?
D plus C.
D plus C, right? Because at worst, you're going to be inserting into the array an item which is a neighbor of your current item and has an edge of length C. It's actually D plus C minus 1, but we won't worry about that right now. Or sorry, it's an unimportant detail. So how can I take advantage of that for space? I can store my array in a circle, right? So if I start with 0 over here, and then I just sort of loop the array around so that I use I use the same location in the array to hold item C, item 2, distance C, distance 2C, distance 3C, and so forth. None of these will be occupied at the same time. Actually, it should be plus C, it should be C plus 1. Right, so arrays of size C, and so that means that I only need C plus 1 space to store my whole array. So that's constant. So now we really have a perfect algorithm, right? It uses a constant amount of additional space plus the N for the vertices themselves, and it uses linear time plus the max distance, right? So in summary, it's order M plus D time and order N plus C space.
Wait, but, oh.
Yes, question?
Question, but I didn't see that you put the N in the front in the space.
Yes, exactly, because we do need to record something for each vertex, right? So notice that, I mean, I started by saying, suppose the weights are small integers, but even if they're big integers, this is pretty good, right? If your C is tens of thousands, it's still going to be dominated by the size of the graph. And this will still be an algorithm that you can't possibly beat with any smart data structure, right? Because the constants are going to be so good. You're only scanning. There's no there's no pointers to push around. There's locality in the scan through the array. So that's a big winner. This algorithm, by the way, is known as Dial's algorithm. It was developed in, when did it, I think 73 or something. Anyway, it was developed back in the good old days when you could make an algorithm that involved nothing more than an array and get it named after you. Right? Unfortunately, now you have to work harder to get an algorithm, to get an algorithm. And actually, I just read a really good article saying that we shouldn't name algorithms after people because then nobody can remember what the algorithm does. But now that we've got this basic idea, let me ask if we can improve this further. And I mean, again, if C is a very small integer, there's really no possibility for improvement. But suppose that C is a quite large integer. Okay. If we look at this algorithm, where are we arguably wasting a lot of space? Or we're wasting a lot of time?
As we scan forward, we may have lots of empty buckets, and that wastes time.
Exactly. So we're certainly not wasting time when it comes to examining edges and updating distances. That's just unavoidable when you do shortest paths. But if I happen to have my edge distances or my existing distances spaced out really far, then I might end up scanning a tremendous number of empty buckets before I get to the next non-empty bucket so that I can take the next step in the algorithm, right? So the question is, might there be some way for us to jump over these giant empty regions, get the scan to the next bucket done more quickly?
Bigger buckets?
Well, we could make bigger buckets, like buckets for more than one value, but the risk there is that now our bucket is going to contain multiple values, and that could, and that means that when we find a bucket, we're going to have to look through all the items in the bucket in order to decide which one to process first, because you have to process the minimum first, right? But let's keep the buckets the same size, but make what you might think of as meta buckets or summary regions, okay? So I'm going to take my bucket structure and layer a second kind of summary structure on top of or underneath these buckets and just mark where I have non-empty groups of buckets. Okay, so this is what's called a two-level bucket scheme. Okay. What I'll do is I'll make blocks of size B, some number of buckets. And I'm going to keep track of non-empty blocks. Okay, and what that means is that for each block, I'm going to need to actually count the number of non-empty buckets or the number of items in the block. And as I add or remove items to buckets, I'm also going to need to update the relevant block. So suppose that I've done this. How can I take advantage of these blocks in order to speed up my shortest path algorithm?
You can first use the larger blocks until we reach a non-empty block, and then go refine the search to the...
Exactly. So on a scan, I will traverse blocks till I find a non-empty one. And then I will traverse the non-empty bucket. To find the minimum item, okay? So let's see what this does to our cost, right? What can we now say about the runtime of our shortest path algorithm if we're going to be using these blocks to skip over empty regions? So we still have neighbor updates. which cost us order M, right? But what can how can we analyze the bucket scanning cost? Well, let me divide it into two pieces. First, there's the block scanning. And then separately, I'm going to look at the bucket scans that happen after the block scans. Okay. So can anybody bound either of these? The work I spend on block scans or the work that I spend on bucket scans?
Well, bucket scans is like O and B because you only have to scan at most n buckets.
Exactly. I only scan B buckets, right? So each time I do a delete min, I only have to scan the buckets in one block, right? Because I find a non-empty block, I know I'm going to find something there. So it's order B per delete min, which means it's order NB overall, right? What about the block scan?
O of NC divided by B, since in the end we reach at most NC in max distance, and each block scan lets us jump B.
Exactly. Each time we skip a block, we're skipping B buckets. And that means that since we go to at most bucket NC, the total block scan time is NC over B, right? So leaving out the M to avoid clutter, we see that we're going to be spending order NC over B plus NB time to do the priority queue operations. Well, we can pick whatever B we want, right? That's just a parameter that we can choose in the algorithm. So what should we do? Well, this is another place where we play balancing, right? We've got an N term in both cases, and then we just have C over B plus B, and we want that to be as small as possible. So we're going to balance by setting C over B equal to B. And that means that B is root C, and we end up with a runtime of order N square root of C. Right? So let's compare that, right? So Dial's algorithm, which was considered so awesome that he got it named after him, that takes us M plus NC, right? But we, with this simple two-level buckets trick, improved it to M plus N square root of C, right?
Can we do even better with like a 3-level bucketing?
Aha, yes. Bucketing? This is exactly the way to think like an algorithmicist, right? If you can do it once, you can do it again, and it's better, right? So how do we generalize this? Well, what we can do is we can put super blocks on top of the blocks, right? And we can scan a super block for a non-empty block. And once we find, sorry, we can scan for a non-empty super block. And then we can scan it for a non-empty block. And then we can scan that for a non-empty bucket, right? And now if you do the balancing, it ends up that you want to set your block size to be C to the 1/3 and your super blocks to have size C to the 2/3. And you end up with an order M plus NC to the 1/3 time for doing your shortest paths. Okay. So now it seems like we're on to something, right? So if you can get n plus nc to the 1/3 using using 3-layer buckets, how can we make things better?
More buckets, more layers.
More layers. It actually means less buckets if you think about it, right? More and more layers. Now, if we do more and more layers, is this going to take us to an m plus n running time? Because that would be pretty wonderful. Because if c disappeared, we'd be linear time regardless of the edge weights.
You'd have to consider the cost of the layers.
The cost of what?
You'd have to consider the cost of like changing a layer from empty to non-empty.
Okay. Well, so changing a layer from empty to non-empty is constant cost, right? I just have to mark it as empty or not. But you're definitely on the right track, right? More layers means more layers that I have to mark empty or non-empty, right? So what happens when I insert an item into one of these layered structures? I may be changing all the layers where that item is from empty to non-empty. So if I have k layers, that means that inserting or deleting an item is going to modify k layers, right? And notice that I insert or delete items once for every edge. So my overall runtime is going to start to look like mk plus nc to the 1/k. Okay. Which is not terrible. Okay.
Can you justify why the k appears as c to the power 1/k? It's not clear to me.
It's a balancing game. So you remember that when we had 2 layers, we balanced this c over b is equal to b to make the time going through blocks equal to the time looking inside of a single block, right? Well, when you go to 3 blocks, you again want to balance the time you spend scanning the super blocks and the time you spend scanning the blocks and the time that you spend scanning for a bucket inside of a block, right? And so let's do this for three layers, right? So if my super block size is B, that is, the super block contains B blocks. And just to keep it from getting too complicated, let's also say that the blocks contain B buckets, the same B, right? So that means that the number of super blocks is going to be NC divided by B squared.
Right.
Right? And so that means that I'm going to want to set NC divided by B squared equal to B in order to balance my costs equal to NB in order to balance my costs again. Right? And so now you're going to set B equal to C to the 1/3. And so it generalizes for any k, right? That you're going to set NC over B to the k to be equal to B in order to get balance everywhere.
But we also have another search inside each block. Inside each super block, I mean.
It's a scan, right? Oh, I'm sorry. So actually, here's the problem. There's also a k here. Because I have to do this C to the 1/k scan at every single layer, right? So I choose a block size of C to the 1/k, but now I have to scan k different layers to find my next item. And I also have to update k different layers every time I insert or delete an item.
No, what I mean is that in a super block, you have to also search among the blocks.
I don't have to search, right? Remember that at each of these layers, right? I scan through the super blocks to find a non-empty block. Once I find the non-empty block, I simply scan it. And all of the items that are in that block will be found in a single scan that only costs me the size of the block.
Yes, but I mean, okay, first you scan through the super blocks, right?
Yes.
And then when we find a non-empty super block, we go inside the super block and scan the blocks. Is that correct?
Yes. And there are going to be c to the 1 over k of those blocks to be scanned.
Like in the three layer case, I think there's an extra cost that we are not considering. Like the NC over B squared is for scanning the super blocks, and the B cost is
actually let me present it to you a slightly different way that I think may make it clearer that I'm accounting for this properly. Because this is actually where this idea heads anyway. It's to something called tries. So a trie is basically a depth K tree over sibling arrays of some size delta. And so basically these are degree delta trees. But since I know that they're going to be degree delta everywhere, instead of keeping pointers for the individual children, I'll just have an array of children. Okay, and they will point to arrays of their own children. Okay. So if I have a trie like this, right? For my application, I'm going to have a range of C possible values to store in that trie at a given time. Here I'm going to be again playing the trick of thinking about things in a circle. So I can store 2C plus 1 in the same place as I store C plus 1, because by the time I'm looking for 2C plus 1, I won't need C plus 1 anymore. Okay.
Right.
Now what I need is for C to be equal to, or C plus 1 to be equal to delta to the K, so that I can store all of my different values in the trie, right? And so I'm going to set the degree to be equal to C plus 1 to the 1 over K power, okay? But ideally, I'm going to make this a power of 2, because that just works really well in practice for aligning all of your arrays. Okay, so let's think about, we can sort of abandon the shortest path motivation now and just think about storing and finding minima in this trie. Okay, so how much time does it take me to insert an item into this trie?
Okay, one for each level.
Yeah, I basically walk down the trie, right? I look in the appropriate array position at each layer of the trie, and that takes me to the next layer of the trie. And eventually I get to a leaf and I put the item in the appropriate bucket. Okay. And the same is true for delete, right? If I need to remove an item from the trie, I just walk down the trie to find it and then I take it out. Okay. But what about delete min? How do I do a delete min? Well, I first find the minimum non-empty child of the root. And how long does that take me?
Oh, delta?
Takes me delta, right? Then I find the minimum non-empty child of that, and that takes me another delta. And I need to do that at each layer of the tree, of the trie. And so overall, I spend K delta time. Okay. So now if we take that back to our shortest path application, right? Our overall runtime is going to be the time for m inserts and deletes. So that's m delta, plus n delete mins, and each of those are going to cost me k delta. Right? Which I can expand out as mc to the 1 over k plus knc to the 1 over k. Right? And now I'm going to want to balance these. Okay.
Wait, sorry, shouldn't insert take k time, not delta?
Insert does take k time.
I think he's talking about like the overall runtime should be mk.
Oh, thank you. mk. Good. So here again, I'm going to balance by setting m equal nc to the 1 over k. And if you do the math, this gives you a runtime. This tells you that k should be equal to log base m over n of c, and your runtime becomes order of m log base m over n of c. All right. So that's a slightly weird time bound. Although we have seen this, this kind of log base m over n before in minimum spanning tree, the point is that if the graph is dense, then this is going to be linear even for quite large values of c. But if the graph is very, very sparse, this starts to look like m log c. So any questions about this use of a trie?
Didn't we get the same runtime bound earlier without the trie?
We got the same bound by talking about these superblocks and superblocks and superblocks, and the trie is just a more elegant way to think about and implement these superblock data structures. All right, so just to summarize, right now we've managed to build a monotone priority queue which had an insert of order k as you walked things down the trie, and also a delete of order k. And a delete min of order delta k. But now's when we start to introduce some more algorithmic thinking, or some less elementary algorithmic thinking. How can we improve on a data structure like the trie? Well, we're going to invoke our important concept from data structures of being lazy and procrastinating and only doing your work when you need to. And I'm going to tell you about a modification by DiNardo and Fox from '79, which does a significant improvement. Okay. So where might we be overthinking, doing too much work in our trie data structure, right? It doesn't seem like we're doing very much, right? On a delete min, we just scan through some blocks, and it seems like we have to because we're looking for the min. How else are we going to find it? So let's focus on the insert, where, you know, when we insert an item into the trie, right, we figure out which top level bucket it belongs in, and we go to the children of that top level bucket, and we then figure out which top level, which bucket we belong in among the children, and we just keep working our way down through the different layers of buckets, finding the next sibling, and so forth. I claim that we are wasting work and we should be procrastinating. What are we wasting?
Well, if the lower buckets only have like one element, then there's like no point to scanning it.
Okay, so we could argue that the first element that goes into this bucket, okay, so again, let's suppose these are, these are my occupied top level buckets, right? The first element that goes in here, why should I expand all of this stuff, right? There's only one element, I could just leave it here, okay? But what about the second, when the second element lands in that bucket, right? Do I at that point need to, maybe at that point I should expand everything to differentiate them?
Well, we expand the next level and see if that differentiates them.
Good. So what you're suggesting is that we should only expand as far as we need to differentiate a pair of items that land in the same top level bucket, right? That's plausible. I mean, it's a good argument for laziness, but let me carry it a little further. Why do we care right now about differentiating these two items?
Yeah.
To keep order between them.
Do we need an order between them right now? So the only time that we actually care which of these items is smaller is when it's time to delete one of them from the list, right? As long as we're just doing inserts and deletes and we're not doing any delete mins, this comes right back to Fibonacci heaps, right? Why work? We don't need to compare things just to do inserts and deletes, okay? So the idea of DiNardo and Fox is to say, well, if our current minimum is in this bucket, then we don't care what the order of things is in this bucket or this bucket. And if we invest work in figuring out which one is smaller, that might turn out to be wasted work because we could end up deleting some of these items before we ever get to this bucket, right? Some of them might be moved to other buckets, right? So DiNardo and Fox's idea is to say, just don't push items down until you must to find them in. Okay. So essentially, we have the try, but we only have one so-called active try node per level. And it's the try node that's on the path to the current min. Right? So, I mean, it's this picture only with we only expand these other layers if this is actually the top level node bucket of the minimum element. And then we go to we expand the top level element, the top level node of the minimum non-empty bucket at each layer. Other items that are not on this path just stay in the bucket of the lowest active node they belong in. So, at the top level, I'll have some other non-empty buckets after the current min. At the next level, I'll also have some non-empty buckets after the first the first min, the first element in each layer. But I'll just store them there and I'll let them pile up, right? Because I don't care how to differentiate the items that are not currently in the minimum bucket. Okay. And what I'm going to do is I'm just going to keep count. And I'll show you why later. the number of items in each layer so that I can quickly notice when I've emptied out a layer. And I don't count my descendants. Right? So in this picture, I have whatever, 3 items, I have 2 non-empty buckets or some number of items in the top layer. I have 2 non-empty buckets in the second layer. I have 3 non-empty buckets in the, or 2 non-empty buckets in the third layer and 3 non-empty buckets in the fourth layer. Okay? And I only expand a bucket when it becomes the minimum. So with that plan in mind, let's talk about how I would implement the operations that I need. So how do I do an insert of an item into this trie? Well, I just start at the top and I walk down until I land in a non-minimum bucket at some level. And then I just stop and put the item into that non-minimum bucket. Make sense? And then I also increment that level's item count.
So you use the representation of that number in the base k of
exactly base delta.
Base delta, sorry.
Yeah, and that's why it's nice to have a delta be a power of 2, is that it's very easy to pull out the appropriate bits of the item in order to figure out which child it belongs in, or which bucket it belongs in.
Yes.
Now the next operation that we need is decrease key. How do we do that? Well, it's pretty obvious, right? We remove it from its current location and we have to put it into its new location, right? Or maybe, right? If you think about it, we might not have to do anything, right? It might still belong in the same place. Now, if we do remove it from its current bucket, what might we have to do? We have to find its new bucket. Where is its new bucket going to be?
Built behind it, or like below it?
Below, exact, behind or below, right? So the new bucket is behind me on the same level. Or below. It may be that I now belong in a bucket that was expanded, right? So essentially, I just need to descend from my current to the new level that I should be on and the new bucket that I should be on that level. Okay. So already I can put together an amortization for the cost of these operations. What is the total cost of insert and decrease key operations on a particular item?
Excuse me, can you repeat the decrease key?
Yes. Let me just finish writing this. So if we come back to this picture, okay, so suppose that I do a decrease key on an item that's here. What am I going to do? I'm going to look up a new value. I'm going to ask, okay, it has a new key. Actually, let's look at one that's over here, just to be more general. So I'm in this bucket right now, and I perform a decrease key operation. So what might happen? Well, one possibility is that I still belong in this bucket. Another possibility is that I've gotten smaller enough that now I should move to this bucket. In which case, I just remove me from this bucket and put me in this bucket, and that's constant time, right? Now, the next possibility is that I decrease so much that I belong in this bucket. Now, if I've landed in this bucket was expanded. So I'm gonna have to drop down and figure out which of these buckets I belong in. Now, that's again constant time, and maybe I land in this bucket, in which case I'm done. Or I land in this bucket, in which case I'm done, right? Another possibility, now can it happen that I end up in this bucket?
No.
That's going to be a disaster, right? If I end up in this bucket, it means that all of this expansion was wasted. But can this happen?
No, because the min is monotone increase.
Right, this is again the monotonicity property, right? So however much I'm decreasing, I'm not getting smaller than the current min. So either I land in one of these buckets or else I land in a bucket that needs to be expanded. So I basically keep going down until I reach a bucket where I shouldn't expand, and then I stop and stay in that bucket. Clear?
Yep.
Okay, so now, what's the total amortized cost of doing insert and decrease key on a single item?
Order of the depths of the.
Exactly. We only ever descend, as I just explained, which means that the overall cost is order k, no matter how many decrease keys we're involved in. Okay. I guess plus the number of decrease keys, because each one of those takes constant time. But the overhead work is only order k. So we've got one more operation left to do. And that's delete min. Okay. So again, we've got our many expanded layers of the trie. And we're currently sitting on a minimum item somewhere. We have to delete it and we have to find the next min. How do we do that? Well, we're going to remove the current min. And now we have to find the next. Where is it? Well, one possibility is that this bottom level still has items in it, in which case we just need to scan forward to find the next one. But another possibility is that this layer got emptied, right? We removed the last item in the bottom layer. Well, that means we have to go up to the next layer. Now, again, there's two possibilities. One is that there are items in this layer, which means that we have to scan for the first non-empty bucket. And when we find it, we have to find the min in that non-empty bucket. How are we going to do that? Well, we're going to expand that bucket to get a new bottom layer. And then we will find the minimum item in that new bottom layer. But another possibility is that this layer is also empty, and we have to go up to the next layer. Right? So essentially, we're going to have to keep walking up until we find a non-empty layer. Then, after we find a non-empty layer, we're going to have to scan for the first non-empty bucket. And then we're going to have to expand down to create a new bottom layer. And reveal the new min. So we have to go up to the first non-empty layer. We have to go over to the first non-empty bucket and then expand down to the next min. So how much time is this going to take? Well, it seems that the bulk of the work is in the expansion of the buckets, but that's already paid for. Because we already said that we're spending k time per item moving down, right? And I previously associated that with the inserts and the decreased keys, but here's another place where the descent might happen, but no matter when the descent happens, there are only k descents per item. So that's order k, and we've already accounted for that. So all that's left is going up to the first non-empty layer and scanning for the non-empty bucket. Now the up costs less than the down that we do when we're expanding things. So we can ignore the up as well. And that means that the only cost we actually have to pay for is the scan, which is delta. So delete min costs delta. And remember that insert costs k. And decreased key costs 1, because we don't charge the descents to the decreased key, we charge them to the inserts. So if you put all that together, you get shortest paths in order m time, that's the decreased keys, plus n times k plus delta, because you do one insert and one delete min per item. And when you balance that out, you get a runtime of order m times log c divided by log c. So on the one hand, it's not a big improvement. It's only a log c. But it still is an extremely simple data structure. And in data structures, log terms are actually relevant, because usually, I mean, basically a log n term in a data structure is like an n term in a runtime of a typical algorithm. And a log term is like shaving off a factor of log n from one of your standard algorithms. So a little bit of work gave you some nice improvement. And notice that even if, for example, C is a 64-bit integer, right? This is still going to be basically a linear time algorithm. So as long as you're working with integers in your shortest paths problem, you're probably better off using an algorithm like this in practice than implementing some sort of Dijkstra type priority queue. Okay. So you might think that we're done, but we're not, because like I said before, theoreticians always like to do more of something. So where is the bottleneck in this data structure? It's in scanning a particular layer in order to find the smallest non-empty bucket. What kind of problem is it to find the smallest value in a list of values? Or to maintain the smallest value in a changing collection of values?
Priority queue.
It's a priority queue problem, right? So it feels like there ought to be a way to somehow apply a priority queue on top of our priority queue in order to improve the performance of this scan for the next smallest item. And I'll show you how to do that next time. So I'll see you on Wednesday.